Hello everyone. Let us discuss the design of IIR filters, and we will start with the first technique of approximation of derivatives. Then we will also design IIR filters using impulse invariant and bilinear transformation techniques. IIR filter design techniques depend mainly on converting analog filter to a digital one. So let us try to understand the process of designing digital filters um, using analog filters. What we will do is we will take the already existing system functions in the analog form, and we will try to transform the already existing system functions to their equivalent digital transfer functions. And we will also work on we will also work on taking the low pass filter prototype system functions in the analog domain, and we will create from low pass filter prototype to high pass and band stop filters. After that, we will apply digital transformations to get the equivalent digital filters. It may be either a low pass filter, high pass filter, band pass filter, or a band stop filter. So that's the basic idea of designing IIR filters we will adopt. Now let's look at the analog filters which can be described by three methods. The first method is by its system function. The system function HAS expressed in the S domain is given by the ratio of two polynomials expressed in S domain, right? The second method is by its impulse response. You see here the system function HAS is related with its impulse response HAT through this integral. Integral going from minus infinity to infinity, HAT e to the power minus ST dt. Right. The third way to represent the analog filters is by linear constant coefficient differential equations. The left hand side of this differential equation has the summation. These are alpha k's are the coefficients, and this is the kth derivative of yt. This will be equal to summation k going from 0 to capital M, beta k coefficients, and the kth derivative of xt. That's how we will see into how we can use the techniques to transform the system functions in the S domain to the Z domain. Each of these three characterizations leads to an alternative method for converting the analog filter to its digital equivalents. The system function HAS is stable if all its poles lie in the left half of the S plane. We all know that. Hence, the conversion is effective if the j omega axis, I'm talking about the S plane, the y axis in the S plane is the j omega axis. The j omega axis, because on the left hand side of the j omega axis, the stability of the system function exists. That means the whole j omega axis in the S plane must map into the unit circle in the Z plane. So if the left hand side of the j omega axis maps to the inside of the unit circle, that also leads to a stable digital filter. The left half plane of the S plane map into the inside of the unit circle in the Z plane, that is, stable analog filter will be converted to a stable digital filter. So this point is very important, right? This establishes the mapping of the left hand side of the S plane to the inside of the unit circle. Now, the simplest methods to convert an analog filter to a digital filter is to convert the differential equation into equivalent difference equation. Now, how to convert it into the difference equation? Let's take the first derivative, dy t or dy t by dt, and we replace every small t with n capital T. That means we are doing the sampling here, right? And we will convert the differential equation into the difference equation. Now this differential, when t is replaced with n into capital T, can be written as y n capital T minus y n t minus t divided by t, right? So this is backward elimination, and this we can, for simplicity, we can avoid to write capital T here, and we can simply write yn minus 1 divided by t. It doesn't mean that we have taken t out and we have divided the capital T in the numerator with the capital T in the denominator. No, no, it's not like that. Just for simplicity, we can avoid to write capital T, and we can write it simply as yn minus 1, and this capital T in the denominator stays as it is, right? Then yt, from yt, this is the analog system function, and we have the differential equation dy by dt, the first derivative that we are trying to convert it into the difference equation. And what is the equivalent? The equivalent of yt in the discrete domain is yn. The equivalent of hs equal to s is hz 1 minus z to the power minus 1 capital T. This we have got after taking the z transform of this factor, yn minus 1 divided by capital T. So yn, if you take the z transform, and you this is yz minus z to the power minus 1 yz, and if you take yz divided by xz, that means if you express it in terms of the transfer function, you will see that it will be equal to 1, because yz you will take common, 1 minus z to the power minus 1 divided by t. So your transfer function hz is basically yz by xz. So hz will be 1 minus z to the power minus 1 divided by capital C. So this basically leads to this difference equation, yn minus 1 divided by capital T. So let's see the equivalence. The equivalence says, for the analog derivative, the system function is given by hs is equal to s. We know from here the system function is related to s, whereas the digital system function is related. What we will do is we will transform this s into 1 minus z to the power minus 1 divided by capital T, right? And which leads to, and if you equate the analog part of the system function to the digital part of the system function, that means s is equal to 1 minus z to the power minus 1 divided by capital T. So this is actually the transformation that results for the first derivative, right, in the differential equation. That means we have to replace every s which is present in the system function by 1 minus z to the power minus 1 divided by capital T to get a digital filter from its analog counterpart. Now let's look at the second derivative, that how we have to convert the second derivative in the differential equation, and what should be the equivalent difference equation of the second derivative. Now this can be expressed as d by dt of dy t by dt, and we know that how to get the difference equation is by replacing small t with n capital T, right? You first express how to solve this. You know what is dv dy by dt. This is yn minus 1 divided by capital T. Then you again take the differential of that. You will see that this will come out to be yn minus 2 yn minus 1 plus yn minus 2 divided by t square. Now, if you take the Z transform and if you try to get the transfer function, you can say that because this is second derivative, so what we are doing is we are looking for the equivalence of s square. This will be 1 minus 2z to the power minus 1 because it is yn minus 1 here, and plus yn minus 2, that means z to the power minus 2 divided by t square. So what is the transformation? In the analog domain, if we take s square, this will be equal to 1 minus 2 z to the power minus 1 z to the power minus 2 divided by t square, and we can express it as 1 minus z to the power minus 1 divided by t whole square. And you see what was the case in the for the first derivative? It was 1 minus z to the power minus 1 divided by t. What is the case for the second derivative? 1 minus z to the power minus 1 divided by t whole square. That means s square is equal to 1 minus z to the power minus 1 divided by t whole square. So in general, we can extend this to a more generalized um, derivative approach, meaning by then the kth derivative is equivalent to frequency domain relationship as s to the power k is equal to 1 minus z to the power minus 1 divided by t whole power k. So if it is s, it will be 1 minus z to the power minus 1 by t. If it is s square, 1 minus z to the power minus 1 by t whole square here, and so on. So this is actually, this will be the transformation that we will use in the method of approximation of derivatives to convert a differential equation to a difference equation. And ultimately what we will get from this transformation is that we will get the digital filter out of its analog filter counterpart using the system function expressed in S domain. And what we will get the system, the transfer function in the Z domain. The system function for IIR filter obtained as a result of approximation of the derivatives is hz. That's what I was trying to explain. We will get hz. This is the transfer function that we will obtain in Z domain from HAS, which is in S domain, by replacing S with 1 minus z to the power minus 1 divided by capital T. So let us investigate the implication of the mapping from the S plane to the Z plane. Now this is the mapping. Actually we will, if you, because S is equal to 1 minus Z to the power minus 1 divided by T, and you can express it in equal to Z also. So Z will be 1 over 1 minus S capital T. And if you replace S with J omega, J capital omega, then the J capital omega axis is mapped to the Z domain like this. Z is equal to 1 minus 1 over 1 minus J omega capital T. Now if you multiply the numerator and the denominator with 1 plus J omega T, you will get this expression. You will get the real part separately and you will get the imaginary part separately. Now the y-axis in the S-plane is mapped into a circle of radius. If you get the mapping from here, you will see that the y-axis in the S-plane is mapped into a circle of radius half. So this circle, this left side is the S. This is the S-plane. Now left side is mapped to a circle. Now what is this circle? This circle has a radius of half. This half radius is there, and with center z is equal to 1 by 2. So with center equal to 1 by 2. So here is the center, right? Because in the z plane, the x-axis is the real part of z and y-axis is the imaginary part of z. So that means at z equal to half, so this is z equal to half, this will be the center of this circle, and what is the radius of this circle? The radius will be half. So all the points in the S left hand side of the S plane will be mapped onto the onto this circle. Now any point in the left hand plane will be mapped to points inside that circle, so the resultant filter is stable. Now the possible locations of poles of the digital filter are confined to small frequencies. Now if you see here, because this is the Z plane and these are the low frequencies, you start from here 0 and this will be Z equal to 0. Then if you take the frequency in terms of frequency, the digital frequency, the small omega will be 0 and you will get very small frequencies. You for after this transformation, the possible locations of the poles of the digital filter are confined to only very small frequencies. As a consequence, the mapping is restricted to low pass and band pass filters with relatively small resonant frequencies in the case of band pass filters. So that means out of this method, you can design you can design only low pass filters and band pass filters with relatively small resonant frequencies. But it is not possible to transform a high pass analog filter into a corresponding high pass digital filter. That's one of the drawbacks of this transformation. Now, in attempt to overcome this limitation, more complex substitutions for the derivatives have been proposed, such as for the first derivative t equal to when small t will be replaced with n capital T. So this is the transformation whereby we can achieve the conversion of the high pass analog filters to a high pass digital filter also, where this dy by dt t equal to nt will be replaced with 1 over t sigma k going from 1 to L alpha k coefficients y of nt plus kt minus y of nt minus kt divided by capital T. So this is, if you use this transformation, we can get the high pass filter designed also. Now the resulting mapping between the S plane and the Z plane is now S is equal to 1 by T sigma k going from 0 to capital L alpha k Z to the power k minus Z to the power minus k. So if we will have to replace every S with this factor, right, to get the transformation. And when we try to get the frequency response of this digital filter by replacing Z with e to the power j omega, so we will get we can prove that if we substitute the value of Z to be e to the power j omega, we will be able to get S is equal to j omega. So that means the equivalence is right there. Which is purely imaginary, which means by carefully selecting alpha ks, the j omega axis can be transformed into the unity circle. This can be done by using optimization. By if you use this transformation, this modified transformation. Now let us look at one of the examples. The example says we have to convert the analog bandpass filter with system function. So this is the system function given 1 over s plus zero point 0.1 whole square plus 9 into a digital filter by substituting for the derivatives method. Now we know that what is the transformation to convert a analog filter to a digital filter is that we have to replace every s with 1 minus z to the power minus 1 divided by capital T, right, where capital T is the sampling period. So you replace this s with 1 minus z to the power minus 1 divided by capital T plus 0.1 whole square plus 9 here. Now if you solve it further, you will see that uh, the final transfer function in the z domain, that means this is the digital transfer, this is the equivalent digital filter, and xz will be equal to this expression. This is the final digital filter after you transform small s with 1 minus z to the power minus 1 divided by capital T. Now t should be less than or equal to 0.1 for, and we can just analyze this expression and we can establish that capital T should be less than or equal to 0.1 for poles near the unity circle. So that means we can decide the sampling time also, whereby, because we have to place all the poles within the unity circle to get a stable digital filter. But that's the trick to obtain the digital filters by approximation of derivatives by this transformation. Now let's take one more example. We will have to convert the analog bandpass filter in the previous example by the use of this mapping now, which actually we propose the modified mapping. So we will use this mapping, and after how to use this mapping, we have to replace. Now this is the transfer function of the bandpass filter given. Now we have to replace S with this mapping equal S equal to 1 by capital T Z minus Z to the power minus 1. So we will substitute by substituting for S in HS we obtain HZ is equal to 1 over Z to the power Z minus Z to the power minus 1 divided by T plus zero point 0.1 square plus 9, and we get this expression or this transfer function, the equivalent digital filter transfer function. Now if you factorize the denominator, if you find out roots of the denominator polynomial, you will see that hz has 4 poles while hs has 2 poles, which means that the conversion has led to more complex system. So this conversion, because of this mapping, has led to a more complex system. Whereas in this case, the if you take the roots of the characteristic equation formed by the denominator polynomial, you will see that there are only 2 poles. So the complexity remains the same. But if you use a modified substitution, modified mapping, then you will get is more stable digital filter within the, because all the poles will lie within the unity circle, and you will be able to design all kinds of filters like low pass filter, band pass filter, and high pass filters also with this mapping. But the complexity of the system will increase. Well, this is the method for conversion of IIR filters, for designing IIR filters by converting the analog, by converting the already existing analog system functions to digital transfer functions. Thank you.